We all know that the sun has been very active the last couple of years, more than even expected. We have seen a lot of aurora, but these phenomena extend also in the radio area, and Hervé will tell us about that.
Yes, thank you, Chris. Good morning, everyone. So for those of you who know me well, you know that my two main topics for work, my two passions, I should say, are meteors on one hand and aurora on the other hand. Usually I have to go really north to observe the second one, but actually lately it was possible to observe also from our latitudes. So I will talk about observations of aurora using our BRAMS network. So making best of both worlds, I would say. So I'll just remind you that the BRAMS network is using forward scatter radio observations, which means that, as you've seen before, the receiver and the transmitter and the many receivers we have are not co-located. So the BRAMS network, this is as it looks like now. So we have the transmitter here that you've seen before, and we have 50 receiving stations, which are the green dots. We are transmitting approximately at 50 megahertz. And lately, if you want to go details, we can talk about it at my poster. We increased the power to 340 watt. All the receiving stations are using the same material that is now, everything is contained into a small A4 size box where we have the computer, Raspberry Pi type, SDA receiver, and we have also a small device that you heard before if you were at previous IMC that we call the BRAMS calibrator. I will come back to that later. So this is what typical BRAMS data look like. So this is 5 minutes duration. This is here I show 200 hertz centered on 1 kilohertz, because that's what the receiver is doing, is shifting down from let's say 50 megahertz to around 1 kilohertz, where all the interesting phenomena appear. So you see the direct signal coming from our transmitter here at 1 kilohertz, airplanes reflection, not so interesting, but they are there, and all the rest are many nice meteor echoes with a really good signal to noise ratio. Signal has increased in power, but also this station is really good in terms of local noise. So you see that all these echoes are really nice and can be used for further analysis. Now this is what happened for the same station 1 day later at exactly the same time. And you see during the aurora, this is what I got. So pretty much everything has disappeared and is drawn into noise that I write into quotes, because I believe this was not exactly noise. So to try to quantify this effect, this is a spectrogram, the same one, but that I enlarge a little bit. So now I go from 500 to 800 hertz, because we sample at 6 kilohertz, we have access to approximately 3 kilohertz of bandwidth. Usually I just show this. This is what you saw before. This is where all the interesting signal appear for us. Sorry, what you see, so these are the interesting signal. What you see here is a parasitic signal. I don't know where it's coming from. And this is the BRAMS calibrator. This is the BRAMS calibrator. So this is a signal that we inject and we combine with the signal coming from the antenna. And this is used for amplitude calibration. Yes, so now usually I use this band between 800 and 900 hertz to somehow measure the noise, the local noise at the station, so that I can compute somehow a signal to noise ratio. And of course I avoid this region, because this one is contaminated somehow by other signals. Now when I do that, usually for these stations I have really low value. And actually, these low values are pretty much a fraction of well, slightly above zero. So on this scale, you actually don't see them. And why do I have such a large scale? Is because during the aurora, this is what I measure. Really strong increase of noise again, at least a factor of 50 to 100, so about 10 dB. So this was really large enough to drown somehow all the interesting signal, including the meteor echo. So I quickly made this made this plot. So this is 10 of May, 11 of May. These are the counts per hour of meteor echoes. And you see the daily variation nicely here. And I pointed here 2 times where the aurora was active. And actually, you can see here there's a dip, because if you look here, you see a nice increase. There was probably a nice increase here as well, but we missed meteors because it was drawn into the auroral noise. And here it's particularly clear when the aurora was extremely strong. So now I want to go a little bit more detail about this noise, so-called noise. And here is again the spectrogram that I showed you before. Now so this is 5 minutes duration here. If I sum during these 5 minutes, here is frequency, and now I have frequency as a function of, well, power as a function of frequency. So this axis becomes this one. So what you see is low level of noise, and the blue part everywhere, except at 1000 Hertz, where we have the signal from the beacon and all the meteor echoes and airplanes, this parasitic signal there, and the BRAMS beacon. So this is typical stuff. Oops, I should do that. Now this is what we saw during aurora. This is during 1 hour. So you see every 5 minutes, you see this noise. And you see that it's quite interesting because, well, first it's really strong enhancement of the noise, as I showed before, but this is structured. This has a width of less than 1 kilohertz, and it's very dynamic also with sometimes multiple sub-peaks that you can see. If it goes up again, you see peak there. Here you see clearly 2, 3 peaks. So it's very structured, it's very dynamic. So this is clearly related to the aurora. So what is it? What did we see in our data? So I look in a little bit into the literature, and in particular last year was a really nice review paper by Labelle, who is obviously a specialist in this field. He has published many papers over the years, and he listed 4 types of radio auroral emissions that were observed from the ground before. And these are these 4. I don't go into the detail because it's technical, but one that caught my attention was actually cyclotron harmonic emissions. So basically, the fact that electrons, when they are coming down into the atmosphere, they are circling around the magnetic field. And, oops, sorry, I can keep this, but you see that they were observed typically maximum at 6 megahertz, so way below 50 megahertz. None of them, I could not find any observations at 50 megahertz. But descriptions of these in the article is fine structures, the width at typically less than 1 kilohertz, and so everything in the article seemed to point to what I observed in the BRAMS data, but never observed at 50 megahertz. However, these observations were always done in the north, so at a much higher latitude. At our latitude in Belgium, 50 degrees, the magnetic field intensity is somehow larger at this altitude. These are the values that you can get. And so if I compute a cyclotron frequency, I can get 7.5, maybe 8 megahertz. So it's still lower, but is it possible that we actually have detected an harmonic, a higher harmonic from this? Because we are quite sensitive, of course. So these are the type of observations that were done in the past where you could see 2, 3, and 4 times the frequency of the harmonics. I mean. So what should I do now? So some additional work. One of the things that we can easily do is looking at the structure of these emissions that I show you for one station, but at several stations that are separated in longitude and in latitude to see if we can see a difference in time and intensity, of course. We can have a look at with a better time resolutions than just 5 minutes, because these are normally these emissions are extremely dynamic. One interesting thing is that our station in Humain, we have one crossed dipole Yagi antenna, so we can measure the polarization. And actually, it seems that from the models for these emissions, cyclotron emissions, you should expect left-handed polarization. So that's something I can check. And what I'm doing now is looking at the integrated total power. So when you see this curve that appears, I can integrate this and using the BRAMS calibrator to calibrate it and transform it to real watt per square meter per hertz. Except that I don't know the gain in the antenna because I was not sure where the aurora was located. However, there is a way to find the exact position of the aurora, which will require some work by looking at a lot of optical observations from the many meteor cameras that we have in Belgium. And I will show you here, for those who were in Humain last year visiting the site, this is one camera that we have, the global from Denis Vida, from the Global Meteor Network. And just to convince you that there was a really nice aurora in above Belgium, really above us on the 10th of May, the night from 10 to 11. I don't know if this will play automatically. Maybe if I do this. Can you start it? Ah, no, it started. It started. Okay, it's okay. So this is a time lapse of the night automatically produced by the GMN system. So this is the beginning of the night. You see a lot of airplanes, meteors, some clouds, thin clouds. But at some point, you will definitely see aurora. You cannot miss them. It's coming here. So this is what we saw in Belgium. I see that very often in Norway, but unfortunately I was sleeping. But thanks to these cameras, of course it's black and white, so it's not so impressive. But you see several times. So you see there again. So this corresponds to the 4 peaks that I see in my data. Although there is also a close. No, this is the 3rd peak, I think. I think there might be even at the end of the night, but that I don't see in my data. But anyway, what I want to say is that there were many cameras and also a mic. We could maybe have a look at the old Sky 7 if they still exist. Because looking at these aurora from many directions, using tomography-like techniques, we can reconstruct the volume emission rates of the aurora and have pictures of actually where these draperies were located. So that I can then use the gain of the antenna in that particular direction. So I think my time is nearly over and my presentation as well. Thank you for your attention.
Thanks, Hervé. Questions? Sis.
Thanks, Hervé. Very nice talk. So I have a question. You mentioned that perhaps you see a harmonic signal of something that should be at 7-ish megahertz. So are there any measurements at 7 megahertz, like from the solar astronomy in Belgium, or that could also have captured this, but not the harmonics, but the original signal?
Yes. I don't know, but that's actually a good suggestion to look at other measurements at lower frequency, but unfortunately you were not observing because you were observing only when the sun is up. So
may I add to one? Maybe the Nancy in France, should he have recorded that over a wider frequency range?
I don't know, but that's maybe a good suggestion to check as well. Yeah.
Okay, another one from me. I got a little chat with my friend Felix Verbelen, who is cannot attend, but who is on the Zoom. And he mentioned that also with the second VVS beacon, we got the same stuff, of course. And it was published, and I will get you the PDF. And I guess he got it over a wider frequency range. But okay, off topic.
Wider frequency range, you mean?
Well, maybe a couple of thousand hertz. Not, of course, still 50 megahertz in that band. Yeah.
Okay, good.
Anything more? Yeah, sis.
With my apologies, but I will bug you until everyone has passed there to get their registration form and to pay their fees if they didn't do so. So you can still see me now for 10 minutes or the coffee break later today. Thank you.